All right. Hi, everybody. I'm Scott Loughmiller. I'm the Chief Product Officer and one of the founders here at Scale. And today I'm going to talk about our automated infrastructure management engine. This is technology we've had for a long time. Really something we've had a difficult time explaining to people and getting people to understand what it is and how important it is. So I'm going to take another shot at that today. And so just kind of turn the clock back to kind of what we were trying to accomplish. We started the company in 2008 with a vision of building a cloud-like solution for running your applications on premises. And the state of the art at that time was a VMware 3-2-1 system, right? 3 servers running VMware, 2 switches, and a NAS or SAN for shared storage. We thought that was a very complicated system. You had to talk to a lot of vendors. You had to have a lot of expertise, sort of put it together yourself. And so we put together a Linux cluster with a custom shared nothing storage stack, a variety of open source packages that more or less work together, and delivered what eventually became known as hyperconvergence. And our target market was the small, medium enterprise. And so we deployed in environments with mostly Windows administrators and some places with no IT staff whatsoever. So if you take a Linux cluster and you put a custom storage stack on it and throw a bunch of open source packages together and you deploy it in an environment like that, what could possibly go wrong? Everything went wrong. The customer environments are terribly complex. They're unpredictable. They're always changing. The environments are hostile. The first on-site deployment I did, I think it was like our 10th customer, was a 100-bed hospital in the foothills of the Sierras. Their data closet was literally a closet, had everything, all the servers running in there. It ran at about 106 Fahrenheit all the time. It was dirty. And the IT manager was a consultant who was the IT manager for most of the places in town, and his office was down the street. External services fail, DNS, time servers, software fails. These open source packages don't always behave the way you expect them to. And when you try to troubleshoot these things, it's super painful, especially when you're remote. So our tagline is simplicity engineered, and we really pride ourselves in being able to come up with simple solutions to these complex problems. And we don't mean that the solution, specifically what we build is simple, it means the solution we deliver to customers is simple. And we worked really hard to make that happen, and I think we succeeded. So it's one thing to say it's simple. It's another thing to have your channel partners, your resellers, your MSPs tell you they agree. We succeeded in this, and I think in a way that nobody else has. If you look at what this survey the channel company does every year, they've been doing it for 34 years. And for over 34 years, we've got the highest rating across any vendor, across any segment for all of time, right? So I can stand up here and say, we have amazing engineers, which we do. And they care a lot about quality, which they do. We have an amazing quality engineering team that writes automated testing. All that is true, but that's not different than any other company, right? Lots of people do that. Lots of people have good quality. How do you get this? This takes something special. And what that special thing is our autonomous infrastructure management engine. What it is a sort of hand-built model of the environment the cluster is running in. And it's built in a way that it's easy to actually hand build this model and think about the state that the system is in. You can kind of think of it like a digital twin, where it's modeling the reality that the cluster is sitting in, including what's happening on the hardware in the cluster, but the surrounding environment. It is deeply integrated into the hardware. This is one of those things. If someone says, you can run our infrastructure package on any piece of hardware you want out there, what are they telling you? They're telling you that the hardware is your problem, right? If there's a hardware failure, that's yours to deal with. For us, we're so integrated in the hardware. We care about the BIOS. We care about the firmware that's running on the box. We upgrade those things for you. We manage it. When there's a hardware failure, we know what's happening and we know what to do to deal with it. It incorporates all this cross-domain information, right? So networking, hardware, environmental stuff like temperature, et cetera, et cetera. We're pulling all of this information in and building a state, a model of the state of the system that allows us to predict and prevent issues, identify root cause, and then automate remediation. So I'm going to go a little bit into how it works. I know I don't have as much time as I hoped. So the most important thing when you're building a system like this is the standard adage, right? Garbage in, garbage out, right? So we have to have good information about what's happening. So the first thing we do is we write collectors. Collectors are very small pieces of code that reach out and pull information like what's the temperature of the drive? What's the temperature of the CPU? How many hard drive media errors have we had? That sort of thing. I'm going to say this compartmentalized comes up constantly. You're going to see it in every one of these stages of development. And the reason for that is what it allows us to do as engineers is think about just exactly what we're working on in that moment. Right? There's a lot of times when you might want to collect some data about the hard drive or whatever, and it's not necessarily the best time to do it. The whole state modeling is the one that decides when that code gets run. So as the developer that's working on collecting that information, you don't have to worry about that. You just have to worry about what do you need to write to collect that information. So just some examples of what kind of things we run and take and data we collect. And that, again, it's just very simple, collect that data. The next, and this is, I think, one of the really cool innovations is, and it's super simple, but we call them check values. They're really just variables, but they're tightly controlled. And along with the variable comes metadata about that variable. Like when was it collected? How fresh is that data? Is it out of scope, right? Is it out of a range? It's a temperature and it's, outside of the Kelvin range. Like, okay, we know that's not valid, right? Those kinds of things. And again, compartmentalized. You can just think about the data. What should be here? What's possible? What could be legit? Some different examples of those. And the idea from this came from an instrument panel on an aircraft, right? So here's your heading indicator. It tells you you're going, south-southwest, but it's also telling you, hey, I have a failure. Don't listen to me. Do not use this data. And that's exactly how these check values work. If the check value recognizes that there's been a failure along the way, polling error, getting data out of bounds, whatever, it's going to raise a condition when you try, or raise an exception when you try to collect or use that data, and that tells you, hey, data is unreliable, and so let's not make decisions based on that data. They're cluster-wide, they're shared across all kinds of subsystems. We use them for all kinds of stuff. They're really helpful, and it's available to everything in the system. Conditions are where we start to get some intelligence. Conditions are what we call undesirable conditions, undesirable situations, and they're just set or clear, right? So it's true or false. True or set means there's a problem, clear means there's not. And they're built-in intelligence, and again, compartmentalized. When you're writing a condition and the sort of decision function for the condition, you only have to think about that. You don't have to think about what else is going on in the system. So here's an example, right? We've collected the data, that's gotten put into checked values, and we see that the system partition on the node is getting full. Okay, so we can raise a condition. The great thing about that is now that with Fleet Manager, that'll bubble all the way up to the top, and you saw those conditions in Craig's demonstration. So let's say we have a collector fail. Now the check value expires, and the condition doesn't get set true or false, it gets set to expired. And so now we know we don't know what's happening with this condition, and we don't make decisions based on that. You can get a list of what's happened in the past with the conditions, which is really, really great for troubleshooting. They have configurable set and clear delays, so this helps with flapping, right? So if you have something that's kind of bouncing around a threshold, it's not going to just turn on and off and on and off. And then they go right into UI indicators, fleet manager, and things like alerts and logs all come from conditions. So one of the things that if you've read some of the reviews of our product that you'll find in our product reviews is that our support is amazing. And our support is amazing. It's the best in the industry. But one of the reasons the support is so good is because anytime support gets on a cluster to figure out what's going on, the first thing they do is run sc get condition, show a list of the conditions, and they can see the system tells you, here's what I think is wrong. That helps you quickly get to the bottom, troubleshoot things, find the root cause, and fix problems. Now we get to the meat of it. And I will tell you that every time I talk about this, people's eyes glaze over and nobody knows what I'm talking about. So if you have questions, this is the time to ask. I really want to get this across. So state machines are the piece, this is the magic of the system. So after we've collected all the data and we've made sure that data is valid and we've decided what's wrong and right with the system, we build a model of what we think current reality is. And we do that in these state machines. And I'll show you an example of this. You won't be able to see the details because they're huge. It's a full model, one state machine with many nested state machines underneath it of the entire, what the cluster thinks the environment and the cluster is happening right now.
How often is that refreshed?
Every couple seconds, probably less than that. It's very, very quick. Data is constantly coming in for the collectors, and anytime new data comes in, that bubbles up, and the state machine will make adjustments based on that. But this is where the magic is, right? This is where we decide what works, where we are, what should happen, that sort of thing. Again, trusted inputs, we're modeling reality. And the thing is, what we've been able to do over the last decade is build a structure that accurately models reality and accurately chooses the right path to fix whatever problem is available. And we've been tweaking and tuning and adding to the state machine for a decade. And so basically what happens is you end up in a state, says here we are, we're in this state. And from that state, we know we can go this way, we can go this way, we can go that way. And that way's the best choice at the moment. And we move to a more desirable state. And I'll sort of demonstrate that a couple ways here in a second. What's really interesting about this is the intellectual property here is not any of this architecture that I explained to you. It is actually the structure of the state machine that we've built over the last decade. And so being able to take our expertise and our experience and tweak and tune this thing for a decade, we've built something really special. And the result is an expert system. So here's this is my kind of slideware demonstration of this. So let's see how this works. So basically, so you have a system, everything's green, right? Everything is good, and we have a drive failure. So the first thing that happens is disk management is alerted. We've got a disk problem. We also have a storage problem, right? We have data that's not mirrored. The system can't replace the physical hard drive. But what we can do is fix the storage resiliency. So we can remirror the data across the system. And that gets us to a more desirable state. We were in a state where we had unmirrored data, now more desirable mirrored data. We're still not perfect. We still have a hardware problem, but for all intents and purposes, we can take another failure, right? Another drive can fail, node can go down, no problems whatsoever. So we're in a pretty good state. Then when the drive is replaced, the system recognizes that, and we go back to our clean state. So just a complete overall picture of the whole thing. So one of the things I forgot to mention is we really start to see the term that we've seen over the last 10 years, there's not been term for what this is. The term that's recently been coming up is AIOps. And we really think this has a lot of that functionality of an AIOps solution and built in to our core product.
have a couple of questions.
Go for it.
So one is when you talk about, I mean, most of what you described is real time, or almost real time. So you're measuring the status of the system. You try to go back to, the perfect state of the system. But I mean, there is other couple of things. One is, using the system to collect the data, store the data, and start doing some analysis on it for the, also historical reasons. So you have a similar failure happening, often. So maybe there is something wrong that you can highlight, and I don't understand if you do it. And at the same time, you can do it across the fleet or across all your customers, right? So you collect all the data, and I expect now.
Right. So that's where we're headed, right? So with Fleet Manager now, we've got all of these clusters of thousands of clusters in the field that are all reporting data back to Fleet Manager. We're collecting that and storing that, and this is not what's in the field and it's running on the cluster. So this is actually running on the cluster. It's running on those 3 NUCs right there. It's running on each of the NUCs out on the desk, right? And the reason for that is, these things can't stop working because you lost your connection to the cloud, right? But what we're kind of next step is we've been collecting data into Fleet Manager for a while, starting to see these failures. And I do think there is an opportunity to apply machine learning and look for, trends and that sort of thing, and build even better state machines that can run locally to handle those errors.
So in your state machines, obviously you've got a really good understanding of how the platform, you want the platform to behave, but not everyone's, what's important may be different from customer to customer. So do you have any kind of allowance to allow, customers to kind of set their own preferences for survivability?
Right. So there is some of that. One of the biggest ones is failover time, right? So this is one where we see wildly different concerns from different customers, right? We have some customers who say, it's really, really important that we have a very short failover time. And my response is, well, that can also be just a switch hiccup, and then you're going to take a bunch of stuff down because all the nodes think they're disconnected, right? And so there's configuration options for that kind of thing. There's a range of it. It's, right now, it's not something you can just go in the UI and turn on. If, you're a larger customer of ours and you need something custom, absolutely. For, the smaller customers, kind of got to stick with the way we have it. But I do think, over the coming years, we're going to see us make available tweaking that stuff via APIs and that sort of thing. So
some of it we expose in an easy way for kind of thinking. I mean,
right.
Letting customers decide in a simple way. This application needs
all the IOP priority, things like that, and then we have a whole state machine that allocates, data placement and stuff to accommodate that. But
yeah, because I can see. So I work in the healthcare space, and I can see that there might be situations where data protection might be more important than availability, even potentially, right? Like I have to make sure that data that has been captured, like it stays available, that change record is important. Whether the platform goes down, I've got to be able to make sure that gets back up, so that I know that these things have happened.
Right.
So,
and there's always engineering trade-offs in there, and yeah, I mean, it's all managed via config file and that sort of thing. So it is customizable, but it's it's not super straightforward from a customer point of view yet.
Sure.
All right. Let's do a demo. So if you remember, Craig unplugged this node over here. So I'm going to plug it back in.
gosh.
And watch the system piece itself back together. So you can see down on the bottom, these are the conditions. So when the customer or when support logs in or a customer shows up, you can see them. Hold on, let me. They're also showing up in the user interface here that we've got a problem. Very clear. Node 241 is down, right? That's our problem. So we get in conditions. Obviously on the back end, we can see a lot more of what's happening. One of the things, there's an expired condition here, clock skew over threshold. So we know that we can't say the cluster is clock synced because one of the nodes is missing and we don't know what the value is for that. So that's expired. So we're not going to try to sync the clocks in that situation because we're just not an option. So over here is the state machine, and so you can see the thing constantly updating what it thinks the current state is. And obviously, it's two things. Like it's too big to show, but also like I don't want to show it to you. This is our actual intellectual property right here. So, but I think at this level you can see how much action is happening, how it's modeling, how things are moving as things recover here.
Have you ever benchmarked that versus like a dumb approach, which is fix on fail with redundancy built in, above that, right? RAID, all the usual stuff, and say, because this is more sophisticated, I am 5% better, 3% better, 10% better, from a cost savings perspective or from an uptime perspective. Have you ever, over the last, Scale's been around for a long time, right? This has been.
I mean,
for 10
yeah,
years.
I don't have numbers for that.
Right.
I wish I did because I think they'd be fantastic.
Because one thing I could say is let's just do it the stupid way, which is fix on fail.
Right.
And have application architecture and have the system architecture deal with that for the most part, with the exception of very rare, weird failures, right?
Right, but I think that's the thing, right? So it's just over time, right? We've added all the rare, weird failures into this, right?
Sure.
And you just keep adding, and and it's one thing, right? If you have a 1% failure rate on 10 clusters, right, it's not a big deal. You have a 1% failure rate on 1,000 clusters, you're in trouble, right? And so you really need to be, really pushing the limits on what we consider a rare, weird failure, because as your fleet grows, those rare world failures become day-to-day issues.
Agreed. But then the question is, are you preventative, right? Or and does that prevention actually
is it working? The question is it working? I think we go back to if you talk to our resellers and our MSPs who are not only they don't have one cluster, right? They've sold hundreds, right? And some of these MSPs are managing hundreds of clusters, and they're all telling us we have the best, most reliable product that they've ever seen.
Or are you prematurely replacing it before? That's why it's reliable.
Proactively replace drives. We
Right. It's like the old NetApp thing, right? When they first came up, the drive would anecdotal email, NetApp, and the drive would be shipped out even before it failed, right? So the question is, are you just replacing it ahead of time when you maybe don't need to, right? That's the because when you have these things, it's always very interesting, and you're like, this is pretty cool. But against what, right? What's the benchmark again?
One measure of that, just an internal measure, which is that we're always looking at the number of support heads versus the actual number of clusters out in the field. And that measure over time, it's kind of astounding, literally how many clusters we can have out in the field with a few sales table, especially when you look at the Net Promoter Score that those guys receive with how well they support the product. I know it's one, at least internal metric that we constantly are using to make sure that we're bettering the product overall with this.
So it's almost pulled itself back together now. I think the last thing that we'll see is it's decided it needs to migrate those VMs back to the nodes they were originally on to get us back to the state of the original state. Sometimes takes a couple more minutes.
When you were talking about AIOps before and collecting all the data back up in the thing, will you start looking at things like predictive failures across things and migrate those VMs if those conditions look like they're going to be met?
Exactly. No, there's some very cool things I think we can do when we get a little bit more predictive stuff. Right now, most of the as we all know, right? Most of the failures are hard drives, right? That's 99% of the time. That's what the failure is. And the industry and us and everybody's gotten pretty good at predicting hard drive failures and getting the drives out of there before there's even an issue. And so that's where a lot of focus has been because that's where most of the problems are. But right after that, it's networking and power supply. It's one of the things I forgot to mention. The power in these places is ridiculously bad, right? And nothing at all like a data center. So.
Even things like memory could be interesting. Like a big thing that we see on our cloud platform is like 90% of the time, like hard drive failures with obviously resilient storage and things isn't so much of an issue with the infrastructure we run, but the biggest failure we see from a VMHA perspective is when a memory DIMM pops in a server. You'd solve that.
Yeah. So we do a little bit of predictive analysis for the memory stuff. You can see those errors start to show up. It's less possible. Sadly, it's less possible on the NUC, and probably more important because they don't have ECC. But we get in there, and but we do have some stuff to sort of mitigate those issues, and even on the NUCs. So,
quick question: is there a level of output that we can see what's running on the left? Or is it what we're supposed to be looking at is in the bottom right?
I mean, I think, here the main focus is that you can see this constantly updating about what it thinks the state of reality is. And the fact that it's just always kind of moving is showing you that it's in real time updating its mental model or digital twin of the cluster and its environment. And then there we just basically have completely moved the system back to 100% green, no issues whatsoever. And everything's back where it started in the beginning. Dave mentioned this, and it's one of the things I want to throw out. One thing that we're moving to is opening this up for either ISVs and software vendors who want to deploy on an appliance, or bigger customers who want to, have 1,000 sites with all the same applications in every site. Right? They can start to write their own conditions and their own state machines to manage. Just alerting up, say like, oh, this, hey, this camera's unplugged or something like that, or even so, go to the next level of this camera's frozen, and it's on a PoE switch, so let's bounce the power, and we can do all of that and help them write those tools so that they can kind of reduce their management overhead across their whole platform, not just our stuff.
No, I mean, I like the simplicity. Like, it's refreshing, to be honest. I mean. Yeah.
That's an interesting one, right? Like when we were first starting the company, we started in the SMB market because we've always been kind of small business people, and I think every founder had at one point ran IT for a small company, and we were like, this is the solution we need for them. But we weren't really against going up market, and every time we would start to go up market, we'd bring in the solution, and the storage admins would be like, I mean, you can't do this. It's got to be able to do that and do this and do this. And they're going, you're going to take my job if we buy this thing, right? And so the complexity sold at those kind of larger enterprise deployments, and while in small medium enterprises the simplicity and the ease of use were really, really nice features, at scale, on the edge, they're table stakes.
Yeah, totally. Yeah, I mean, even the little things like you supporting the stack all the way from the bottom to the top. Like, I'm sure most people in this room have been on a support case with another hypervisor vendor before, and then they blame the hardware vendor, and then you go to the hardware vendor, and they go, you're not on the latest firmware, and then you go through like I did it 2 weeks ago, man, and you're like, no worries, I'll update it to that, and it's the support cycle is just so long.
Well, and that's the thing, when you come to us with a problem, we own it, right? We own it's our hardware, it's our software, all the way up to your application, right? So if you have a problem with the infrastructure, we grab that problem, wrestle it to the ground. It's another reason why everybody raves about our support.